our next speaker is Barish, another person I enjoy introducing because once again, I can ignore all the awards, distinguished chairs, honorary degrees, because there's one prize that stands above all others. It's the 2017 Nobel Prize in Physics, which he won together with Ray Weiss and Kip Thorne for decisive contribution to the LIGO detector and the observation of gravitational waves. And that's truly one of the remarkable, amazing achievements of the 21st century. And I can say that even though we're only 22 years into the 21st century. Prior to switching to gravitational waves, Professor Barish was a leader in experimental particle physics. Today, we will have the pleasure of hearing him explain gravitational waves and multi-messenger astronomy. And after the break, this will be followed by two talks from young professors in the Baumick Institute on theoretical research related to gravitational waves. Please.
Morning. First, let me say I'm very happy to be part of this event, tribute to Mani and the Theoretical Center, which is now 5 years old. Also, I'm very impressed at this conference center that UCLA has built. I also apologize for the fact that I'm only here for my talk, and I hate people that do that, but for the first time in 2 years, I've started to travel. And I just came back from a trip, actually overlapping Steve in Spain, and I'm off for another one right after this meeting. Talking about gravitational waves today, probably the best match to the audience would be to talk about general relativity, but I'm not going to do that. Gravitational waves kind of maybe breaks in terms of where we're going and what we can do into three areas. One is tests of general relativity, especially in the strong field limit, where we can really test the equations of Einstein versus any alternate theories. We haven't gotten as far along on that as I'd like, so that'll be another time. The second area is really looking at the sky in a new way with gravity instead of with electromagnetic waves, whether we're looking at dark matter or the early universe or whatever, or dark black holes. I'm also not going to talk about that. I might have, but I've chosen to talk about instead the overlap region between doing astronomy, if you want, with gravitational waves or maybe neutrinos in the future, and what's been the tool that we've had, which is electromagnetic radiation. This is an emerging area. We just have a few examples now, but I'm going to try to show you why, what will be done, I think, and what's going to emerge in the next, in the future. So just reflecting back on astronomy a little bit, modern astronomy started in 1610 when Galileo, for the first time, looked at Jupiter with a telescope that he put together. He didn't invent the telescope, but at that time, it was possible to make a telescope that was pretty good because people had developed lenses for glasses that were better than before. And so he made a telescope good enough to look at Jupiter well, and he saw what he thought were four stars moving around. And that was interesting, but he monitored it for a few days and recognized that the four stars didn't just move on independently, but were attached to the orbit of Jupiter. And he discovered the four moons. Now we know there are more, but 4 moons of Jupiter. that was really the beginning of modern astronomy, where we learned about astronomy with something beyond the naked eye. And now we've had 400 years of astronomy, and we've learned a tremendous amount. I'll address not that in detail, but really the tools. So that's using photons. Astronomy, as we look forward in the future, can use more than just electromagnetic radiation or photons. We've already learned quite a lot from using cosmic rays. We learn a lot of physics from cosmic rays because they interact in the atmosphere and are at much higher energy than particles, than accelerators. And so there's a lot of physics, but there's also cosmic rays that point to sources or give us information by what's emitted from sources. So cosmic rays are our second astronomical messenger. The third one is neutrinos. And neutrinos come from, of course, all the nuclear interactions and so forth in stars or anything else that's going on in astronomy. And we're starting to have large enough detectors to be able to use neutrinos to do that. That's a very hard way to go forward because neutrino cross sections are proportional to mass. And so there's no way to make better technology. You just have to make bigger and bigger instruments. And that's difficult. We're already making a huge instrument under the ice at the South Pole and another one in the Mediterranean. The last is gravitational waves, which is the field that's just barely beginning. And I'll give you some sense of what we can do. And I'll concentrate on gravitational waves because that's what I know. I don't have to say very much about photons. Of course, we're all familiar with that. They are important, the important tool because they point to where things are coming from. So using photons points to wherever something happened that we want to study. Secondly, they're very easy to detect, not like gravitational waves or neutrinos. We can study them both by instruments here on the Earth's surface or in space, and both are managing to give us a huge amount of information. And lastly, we can study it at different wavelengths, not just the visible, which is what Galileo did. So, and there are large new instruments that are going to move us forward, I think, very significantly just in astronomy in the coming decades. I give two examples here. The Rubin Observatory, which was previously called LSST, is just being commissioned in Chile. It is the largest sensor ever put together, most accurate. But the point that I'll make is it's a new kind of way to do astronomy where you have a survey instrument. So it surveys as large a part of the sky as they're able to technically now over and over and over again, looking for changes as a function of time. And that's just emerged in the last decade with instruments that already existed being used for it. This is the first really ambitious instrument to have a survey instrument that was really designed for that purpose. The second example, obviously, people read the newspapers now, is the James Webb Telescope, which has gone through all its commissioning steps now and gotten to L2 in space, and will be our second big telescope in space, but first real instrument looking detailed in the infrared. So astronomy itself is going to be very exciting in the coming decades. In my view, the biggest advance in astronomy and what gave us so much information in the last maybe 50 years was developing instruments that went beyond the visible. We know, I show here the different wavelengths from the radio to high energy gamma rays, but now we do astronomy by looking at all these different wavelengths, maybe the same source. I just happen to show the Crab Nebula here, where we look with different instruments and different wavelengths, and putting that all together, we can try to understand the dynamics of whatever it is we're observing in astronomy. That's about all I'll say about astronomy, except one more maybe footnote, and that is as we came into the 21st century, we've seen another adventure, which is combining instruments rather than combining different wavelengths, for example. And that was taking the radio telescopes, 7 of them, spaced around the world at different places, never made to be used together, but by a lot of hard work and cleverness, they managed to be pulled together to act as if it's one radio telescope almost the size of the Earth. And with that size as a radio telescope, we all saw in 2017 this beautiful image of M87, which is a black hole that is the most prominent one that we can see. It's 55 million light years away from the Earth and 6.5 billion times the mass of the sun. Just a couple of weeks ago, we saw a second picture, which looks almost the same to the newspaper picture, which is an image of the black hole at the center of our own galaxy. But the parameters are really different. You should realize that it's only 27,000 light years away from the Earth, and it's only 4 million times the mass of the sun. So this technique is able to do this huge range of possibilities. Now what they're doing is at least proposing, they're not funded yet, to build their own. They used other people's devices so far completely. They want to build roughly 5 to 10 new modest size, maybe 10 meter or less, telescopes put judiciously around the world. This will enable them to make the images more quickly. They like to say then that they'll make movies instead of stills. It's of course stills spaced by minutes instead of a day. And that will enable looking at the surface of black holes, for example, to actually study the physics of them. So, astronomy is doing well. The second source is cosmic rays. And in cosmic rays, we have pretty sophisticated instruments. In terms of understanding cosmic rays themselves, the alpha magnetic spectrometer, this is SAM-TING, which has been sitting now for a decade on the International Space Station, has completely written the textbook on what we know, what we have in terms of cosmic ray measurements. There are big questions which are not well answered. What is the origin of cosmic rays? What's the physics of how they're made at their sources? How do we make cosmic rays of such high energy? They're much, much, much higher energy than anything we can make on accelerators. And they, again, represent the possibility of giving us signatures of new physics. I'll show you two examples. This plot, which is maybe 20 orders of magnitude in intensity and more than 10 in energy, is the cosmic ray spectrum. Over that distance on a log-log scale, you can almost see no structure, but I point to two structures. The first one, which is well recognized, is what is called the knee on the distribution. It breaks if you actually look at it carefully. And that represents when we believe when cosmic rays start to have enough rigidity that they escape the galaxy. And then way down at super high energies, there's what's called the foot. And that breaks the other direction. And that is believed to be indicative of when you're starting to see cosmic rays that are extragalactic. So that's the cosmic ray spectrum itself. The plot on the right is from the experiment on the International Space Station, the AMS experiment. And it by itself fits a particular model of dark matter. It's the positron distribution. I won't go through in any detail, but basically it is anomalous compared to all the predictions of what a positron spectra should look like, and fits well a particular a dark matter model. Okay, neutrinos we're getting pretty good at doing neutrinos. I'm not sure how much better we can get in the future because of what I said. The cross sections require larger and larger detectors. The biggest advances have happened over the last decades. We're understanding neutrinos from stars or from our own sun. And that is the burning cycle of the sun, which is a fusion process, emits as it goes through all the chain of it, all the different neutrinos of different energies, which have now been measured. Using the big neutrino detector in Japan, they've actually imaged the sun, which impresses me tremendously that you can see neutrinos from the sun and actually make an image just like you do in astronomy. And these detectors are being made larger to study neutrino oscillations and to do astronomy in the coming decade. And so I think we'll see more. We have seen a little bit of astronomy. Neutrinos from a blazar have been identified and written up in Nature from the ice cube experiment at the South Pole. And that experiment and the one in the Mediterranean are proposed to be made about 10 times bigger than they are now. So we will see more on neutrinos. The last messenger is gravitational waves, and I'll spend the rest of my time talking about gravitational waves, pointing to the astronomical effects. First, to remind you that the picture, the data shown on your left is our first observation of gravitational waves. The top one is the data with nothing done to it, just the way it comes on the instrument from the Hanford experiment. And the second one, the Livingston one, and the two put on top of each other with a slight slight slide for the velocity of light, the different arrival times, and they fit very well and so forth. On the right, that's the only thing I'll say about Einstein's equation. If you look at the first panel, that's our data. The second panel is Einstein's equations, fitting the parameters that I won't go through today that we've seen. And if you subtract one from the other, the third panel, which is the kind of thing that an experimentalist like I look at to see whether there's any trends beyond what statistics tell you, is just random noise. So when you subtract one from the other, it just gives random noise. What happens in these, what we're seeing in this is the in-spiral phase, which happens when the two objects are going around each other. There's a lot of parameters. There's the parameters of, what kind of orbit is going around each other, the spins of the initial objects, the spin of the final object, whether there's any precession in the orbit, and so forth and so on. That is the kind of thing we're measuring now. I'll just show you a little bit of what the handles are on that. The merger itself is, of course, where we have the strong field and can test general relativity. I won't talk about that today, only to say that we haven't yet seen any violation at all from Einstein's equations. And then finally, the system has to settle down and it rings down in a characteristic way. The picture on the right just shows that depending on the masses of the objects, if they're light, they go to higher frequency before they merge than if they're heavier. And our instrument, which is just what we can build here on the Earth's surface, is where the Earth is quieted enough for us to make a sensitive instrument, and that's the audio band. We've learned by evolution, our ears, that the Earth is quiet in that band. We have nothing to do with audio, of course, but a quiet environment is what we need. So our instrument goes from roughly 10 hertz to 10,000 hertz. The heavier objects only make a few, like the first one we observed, a few cycles when they enter at 10 hertz, and the lighter ones are in from up to very much higher frequencies. Okay. Just to point out that there's a lot of information in this waveform. People say one event, you don't have much, but in one event, looking at the waveform, you get all the information from everything from the masses of the objects. We can tell the precession, the spins, and so forth and so on. This is just the first term in what's called the chirp mass, the merger of the two objects. And from that, we can calculate the various parameters. This is just the one for the very first event. The fact that the masses were roughly 30 solar masses each. The two masses added up to 65 solar masses, but the final object was only 62, which meant in something like 0.2 of a second, 3 solar masses of energy went out in the form of gravitational waves. This one, this is just a few events from the beginning, just to show you that they come in different forms depending on the masses and so forth, which now we're putting together to try to understand the origin of these black holes. It's not the subject for today. On the lower right is a very different form, something that stayed and oscillated not 5 times or 20 times, but more than 1,000 times, and for more than a minute instead of 0.1 of a second. And that was the first observation of 2 neutron stars merging. Not being black holes, those do make electromagnetic signals, and that's I'll talk about in a minute. Let me just say that even the beginning, you learn something about astronomy by having a different kind of probe. So what did we learn with the very, very beginning of observing these stellar black holes? First, that they exist, of course. They'd never been observed directly. That they come in pairs, binary pairs. That they merge at some time scale that's clearly within the lifetime of the universe since we see them. And that there's heavy ones, that they're more than 20 times the mass of our sun. And that was totally unexpected by astronomers. Why? Because stars are unstable when they get very heavy. And these are believed to be from the collapse of a star. So we still don't understand yet why there's such heavy black holes, if they are stellar, or why they're, and there's different explanations. Our work now involves getting enough events so we can understand where they are, what their mass distribution is, how their spins are, and how asymmetrical they are, and so forth and so on, to try to understand whether some might have come from primordially, some maybe from the collapse of stars, or dynamically, that they build up each other in some dynamical way. There's different models which we're working on. In order to do astronomy the way we talk about and what the title of my talk, we have a big challenge, and that is how can we somehow, it's hard enough to detect gravitational waves, but confidently determine that we have gravitational waves fast enough so that we can alert astronomers that we can look at the same time, because they have to do something. We look at the whole sky all the time, but astronomical instruments have to point typically. And so we need to be able to alert them. That's been a huge challenge, and we've worked really hard on it. And that is, how can we confidently know we have a gravitational wave event fast enough to alert astronomers? We have to do that within a time scale of minutes. We can't make too many mistakes, because if we alert them and they turn their instruments and then we go, oops, too many times, they're not going to do it. So we have to be fairly accurate. In our last data run, just before the pandemic, we had something like 100, just under 100 events. We identified about 80 of those online quickly, and we made about 10 mistakes. So basically in the quick stuff. That's just on the border of what we needed to have confidence that astronomers are willing to look. They want a lot more information, of course, to decide whether they want to look than we're comfortable giving, because it's easy to tell we saw something. It's harder to know what it was quickly and so forth. Anyway, it takes us weeks and months to actually fit in detail to Einstein's equations and end up with the data that ends up in our papers. So one thing is to be able to decide quickly. The second is we have to point well in order to correlate with astronomers. LIGO is just 2 instruments. So 2 instruments, we compare the time when the signals arrives in the 2 instruments, comparing the time. If that's all you did, you'd get a cylinder, a ring in the sky of the location. We do better than that by doing the waveform shape at the beginning and the timing on the timing. And so we get part of the ring in the sky. But you can see these big rings basically that were what we got. Fortunately, we had competition, which managed to work a few years after us. So we made the discovery first, which is in Italy, called Virgo. And once we have a third detector, we can triangulate just like a sailor does. And once we did that, we get 10 times better resolution. So we went from roughly 1,000 square degrees, which is useless for astronomers, to now typically for our events getting tens of square degrees. And that's shown in this picture here. Once we have tens of square degrees, that's good enough to tell astronomers. I just might comment that all the black hole events that we have now, which is about 80 some, there's no reports in the literature of anybody seeing any electromagnetic radiation. So far the black holes are black for astronomers. So the location is then done by triangulation. And we did this soon after the Virgo detector joined us. They're not as sensitive as LIGO, but it doesn't matter. You can have the sensitivity to see the gravitational waves we can do with the one that is best. We just need to locate otherwise. And we can locate as well as I showed you by this process. And soon afterwards, this is 2017, we saw a signal in the 3 gravitational wave detectors. We're able to tell where they were in the sky. You can see LIGO and Virgo in this picture. And at the same time, it turned out that the Fermi satellite was looking at the same region in the sky. Total luck, but they were looking in the same region of the sky. Interestingly, they pointed to the same region and saw a signal. We pointed better than they did, which gave me personal satisfaction since astronomers kept telling me we could never point well enough for them, but that's just a personal note. If you look at the picture on the left, on the bottom is the time frequency signal from this neutron star merger that I showed on the bottom right of the earlier plot. And it comes at a certain time. Time is going to the right. And on the top is the signal seeing the high energy gamma rays from the Fermi satellite. And you'll see that the signal is detected in the high energy gamma rays 1.7 seconds after the gravitational wave signal. It's expected to be later. The gravitational wave signal comes from the merger itself, and the gamma ray signal comes from the nuclear physics after it's merged. So we don't know how much after, but it depends on the models and how well you understand things. But interestingly, in analyzing this event, I'm not going to go through that in detail today, it's 150 million light years away. 150 million light years is 1.5 10 to the 15 seconds. So that means that we, just looking visually here, have determined that electromagnetic radiation, or gamma rays, and gravitational waves travel at the same speed to 1 part in 10 to the 15, which is just an interesting byproduct. Of course, in Einstein's equations, they're supposed to both go at the same speed, the speed we call the speed of light. Anyway, making that observation, which we were fortunate to do, we then alerted the astronomical community. There's roughly 4,000 instruments in the world that are instruments that aren't just small or private. More than 2,000 of them turned and looked in this direction, or if they didn't have to turn. That's the largest mobilization ever of astronomers, of astronomical instruments. We did it for everything from visible, radio, X-rays, gamma rays, neutrinos, and so forth. Took the data, and it's been analyzed in great detail. I'm not going to go through that in detail, but the signal was seen over from high energy gamma rays almost right away, 1.7 seconds, all the way to the radio afterglow 2 weeks later. The whole brightness and forms have been fit to the various models for what happens when two neutron stars merge. And there was a model in the literature which fits quite well. Whether it's right or not, who knows? It's one event. But it's called the kilonova model, like a supernova for the collapse of a star. So the kilonova model fits very well, and it has an interesting feature, and that is this is just the color curves, the light curves to show how well the data are. The data are the data points and colored, and the lines are the predictions of this model. And basically the emission versus wavelength. Interestingly, it's only one event, appears to be a better solution to a problem that's existed for physicists for a long, long time, which is how do we explain how the heavy elements, heavier than iron, got into the Earth when it was formed. We know the universe is primarily made out of hydrogen and helium. That when a star burns, it burns by the fusion process. Fusion starts with the light elements and works its way up to iron, and then basically the star then has burned up the fuel it can use, and it collapses in a supernova. So how did the heavier ones ever get made that got into the Earth? We know how we make them in the lab. We made the periodic table go up to very high ones, usually by experiments where you bombard a heavy element with a lot of neutrons, and then you get a heavier one and it builds up the plot. But in nature, how it was in the Earth has been explained in the past by kind of a complicated argument that in a supernova, there's a process called the Arra process in nuclear physics that's enhanced and makes somehow more heavy elements. So there is ways kind of secondarily to do that. But it turns out that these heavy elements like gold that we like so much, or platinum, are pretty explainable by how many were made in something like 100 Earth masses in just this one collision that we saw. Of course, it didn't make the ones that are in the Earth, but earlier versions of neutron star mergers. We've only looked so far at one class of sources that make gravitational waves. It won't be long, I think, before we see others. Supernova or gamma ray bursts are another example, are signals that give more like a burst signal rather than a form that I showed you. And predicting when we can see them in our own galaxy, we haven't seen a supernova since Galileo, even though we predict it should be higher than that. There is one type 2 supernova per year out to about the Virgo cluster. What it depends on for us, when we can see them depends on how asymmetrical the collapse is, how non-spherical it is. And we don't know that. We know it's got some non-spherical component because when a star collapses, the final neutron star, whatever it is, moves at an average velocity of a few hundred kilometers a second. But the best models for a supernova are basically done spherically symmetrically, so they don't give us information. I don't know when we'll see that. If there's one in our galaxy, I think we'll see it easily. We do a lot of work to try to see pulsars, which is something that once we see them, isn't like the signals that we have now, but are continuous. So a pulsar is a spinning neutron star in our own galaxy to the extent that it isn't totally spherically symmetrical, that it has some mountains on it, we should be able to detect them. So far, we haven't. The ones that are the most well-known by astronomers are also going to be the most spherical. They're the oldest ones and have a constant frequency. So detecting younger ones is probably what we have to do, but that's a very, very difficult job when we don't know where to look, what the frequency is, and the tracking for how it's going around the universe. The last source is the signals from the early universe. And that's probably the most important if we can ever do it, because gravitational waves are the only possible signal we have that actually isn't obscured by the early universe itself and can go back to early times. We're now looking at building up the distributions of, for example, the black holes. What I show here is just the first 60 or 70 events and where they were as we build up the data out into the universe. There's no evidence for them clustering anywhere yet. And we measure things like the spins and masses and correlations. This is all an attempt to start to learn what the sources were of these black holes. Of the 100 events that we have so far, we have a few that we call exceptional events. That is the ones that don't fit the picture of just being black hole mergers or neutron stars or neutron star black holes. We've seen all three of those. We have, for example, and I show it here, a couple examples of events where the object is too heavy to be, if our measurements are good, too heavy to be a neutron star, but too light to be a black hole. There's a minimum believed to be 3 or 4 solar masses to be able to be a black hole or truly be a black hole. And then a neutron star is 1.4 times the mass of our sun. And we have a couple events. We don't have much yet. I'm just teasing you. We also have very, very heavy events. There's a lot of interest in trying to understand whether there's very intermediate black holes. That is not the ones like the center of the galaxy and not the ones like the ones that come from a supernova. And we have an example that's hard to explain. It's a 85 solar mass black hole combining with a 66 solar mass black hole, making 142 solar mass black hole. That is assuming that what we saw is what I said, and that is the signal doesn't look quite like the one you've seen before. It's not going to because it's so heavy. We only see the last few cycles when it enters our apparatus. So it's possible that we've seen something else, but and there are various papers that people have written already saying it's something else. The future is, I think, exceptionally bright in terms of how this field will evolve. I come from particle physics, and particle physics is very limited by our ability to both make a new accelerator, but also the fact that when the Higgs boson was discovered, it was a 2% effect on top of a large physics background. So progress since then, even measuring the spin, has been hard. The difficulty being that no matter what you do, it's 2%, you can make another accelerator where it might be cleaner. In our case, although it's been very hard to detect gravitational waves, the background is not physics, it's purely technical. It's how much the Earth shakes, it's background noise. And so each time we identify what is the limiting background sources, if they're technical and we're good enough, we can make them better. We also have another feature, and that is that gravitational wave signals, when they're measured, we measure an amplitude, not a power. And so that means that we get half the size signal if we move a factor of 2 further out into the universe, but we see 8 times more volume of the universe, so there's much more data. This just shows how quickly we've increased the data rate, even though we don't have that much data yet, in the first 3 data runs. we've been now off because of the pandemic, but when we turn back on early next year, we'll, I think, be very close to one example of a gravitational wave event each day. The pointing that we have now, we were very lucky on the event that I showed you, is in the upper left-hand corner, how well we do. We just happened to be somewhere where we had good pointing because of where the Northern Hemisphere detectors are. But there's two more detectors being commissioned now, one in Japan and one that we're building in India. So by the mid-2020s, our ability to point will be like the lower right-hand picture. And that'll be good for any event and for astronomers anytime. We also are conceiving of how you make a better detector, or a third generation detector. And there's two models for that. I'm not going to show the difference. One is to make things better by going deep underground like they have with accelerators, and the other is to just make it bigger. So we're looking at making it bigger. The Europeans are looking at putting it underground. We'll have to bring that together, but there's some technical improvements that'll make it much better. First, making it bigger makes it better. But for example, everything so far has been done at room temperature. If we can cool, then we can make it much quieter. The limitation from KT noise just in the mirrors themselves is a serious limitation now. Cooling isn't simple. We have to cool without shaking anything, because this is kind of what we do in a precision experiment like this. And we need to have the right materials to make the mirrors out of. So the mirrors that we use at room temperature are fused silica, and we have a coating that works on that. But if we go down, so we have a rather extensive and ambitious R&D program to optimize what temperature, what materials to use to cool, but there's a huge gain in making a quieter detector once we can cool. This is just a picture of the European European design for an underground detector, which will be shaped like a triangle rather than an L shape like ours. Then you can run the beams around both ways, and it's very powerful in terms of the optics. One thing that you can do once you make the next step is move from basically just pure astronomy to at least starting to do experimental cosmology. For me personally, I think that's the real future. Is cosmology is limited by, it first is a bit incredible in the last decade or two, but is limited with photons because early in the universe was totally opaque. So you can't go back any further than 400,000 years from the Big Bang. Eventually, with gravitational waves or with neutrinos in principle, you could go much earlier. But already in this next generation, we can go to much larger redshifts, if you want. The redshifts that we have now are essentially one, and we can go to redshifts of 100 or so. So the next generation detectors I just show here will go back to some finite z's of 2, z's of 10, something like that. And once we go to that's the ones now being just improved, the ones that we have. Once we make the Einstein telescope, or our version in the US, we can go back to almost the edge of the universe, to a z of 100, and start to actually do experimental cosmology with gravitational waves. Lastly, we will do just what is done with astronomers, look at different wavelengths. I mentioned that we can look at the audio band. That's what's available to us on the Earth's surface. But in space, similar experiment has been technically already demonstrated in a test flight and is scheduled by the European Space Agency to be flown in the early 2030s. And it consists of a triangle with, I'll show you the frequency bands in a minute. A third approach is to use the fact that pulsars have very good timing. If we look at the pulsars very accurately, that we see an array of them, and then a low frequency gravitational wave comes through, it screws up the timing. If you know what you're doing, you can then reconstruct that that came from a gravitational wave. So in the end, that enables us, in principle, to cover a wide frequency band, which I show here, just like for astronomers. On the far right is LIGO or advanced LIGO. In the middle is what is the frequency band that's available in space. So we do 10 hertz to 10,000 hertz. They can do 10 to the minus 2 to 10 to the minus 4 hertz, or 10 to the minus 1 to 10 to the minus 4 hertz. And the pulsar timing arrays can do even lower frequency. So we'll eventually be able to cover the large frequency bands just like for astronomers. And with that, I'll end. Thank you.
That was really great. Thank you. Are there any questions before coffee? Maybe one in the back there.
Hi there. Thank you for a very great talk. So I saw that you, toward the end, you mentioned you haven't really gone too far back in the redshift, but I was wondering if you expected or have seen any sort of trend between redshift and number of events or frequency of events.
Yeah, of course, now we're essentially at Z of 1. So we see no trend, but we're covering such a small region that we don't know. That's important, for example, if we try to distinguish where these black holes that we see are coming from. So one of the handles that we might have right now, the main handles we're using are kinematical ones. You know, what are the initial spins? Are they correlated? Is there any precession? Stuff like that. But getting some range of Z, I think, is a really important step in understanding that.
So was it surprising not to see radiation from black hole mergers? Or did you expect not to see any?
Well, they're called black holes for a good reason. There's, of course, some radiation. There's supposed to be some, but so it's not like really the most sensitive tests have been done to see whether there's any. What I'm saying is standard astronomical instruments haven't seen the kind of radiation that they would detect. So that's maybe a little different than some pointed instrument that was trying to see if anything comes from the surface of a black hole.
Just one more, and then it's coffee time.
Sure.
2 months. What are the limiting factors?
The problem is it's difficult to calculate the waveforms accurately with Einstein's equations because we have to first come with the biggest signal comes in the part that's hardest when you start to have strong fields. And so you have to use numerical relativity to calculate even the parts that I showed. And then eventually you get in the strong field part, but to find them, we have to use numerical relativity. Using numerical relativity and calculating all these templates, which we use to compare on computers, was an enormous problem, how to do that. And that was only solved 5 years before and well enough so we could develop. We use 200,000 templates to compare with every piece of time data. So, and those are not perfect even now. For example, if the mass difference between the two is very large, it's really hard to calculate what the signals will be like well. And incorporating the spins in different spin directions is also very limiting.
And
So we do it kind of in a way that maybe can be improved in the future, but it's a hard problem.
Could you use AI somehow?
Use what?
AI to learn forms?
That, yes. Well, that's a whole other subject, which maybe we won't talk about, but let me just say a couple of words. I'm a big, it's kind of my hobby these days is machine learning. And we're trying to use it everywhere right now. For example, we have a very long time employees. People have loved working on LIGO. You go in the control room, and the same people have been in there for a decade. Yet it seems to matter whether person A or person B is in the control room. We do better when person B is in the control room, which tells you something's wrong. And so we're using machine learning, which hasn't been done very much, to do a better job of operating complex instruments, something that I've been working on very hard. A second one, which is really interesting, I think, is that we look for unmodeled sources. I mean, who says everything we know comes from electromagnetism? So how do you look for what you don't know, what it's going to look like? What we do is we use a mathematical form, which is just maybe not the best thing to do, but it's based on wavelets. But wavelets, you can't just use wavelets. We have to use it in some way that has some assumption. So it's not necessarily the right way. And so I think the best place where machine learning can maybe do something that we can't do at all is to find unmodeled sources, things that we don't know just from the experience of looking at the sky and looking at different shapes without bias. What it would mean for machine learning to discover something when we use, Newton's scientific method, or now in modern day statistics, to believe experiments when we've made discoveries. Can we really make a discovery, physical discovery, with machine learning? I don't know. But anyway, we're trying to use it, forgetting that philosophical question, to find sources that aren't known.
Well, let's thank Professor Barish again. And today for coffee, the doors are open, so you can go outside. That's probably a good idea. And if you had a lunch card yesterday, you can get one today at the desk.